Hey everyone, in this video, I'm going to go over the ATC worksheet 2 for Chem 118C. So I'm going to go over the practice problems for this worksheet and the concepts at the same time. So for part A, we see that we are given CrO3, H2SO4, and H2O, aka Jones, as the first step, which is an oxidizing agent. So we see here that we have a primary alcohol, which will get fully oxidized down into the carboxylic acid. So this carbon here that's attached to the primary alcohol is this carbon here of the carboxylic acid. Then in the next step, we see that we use SOCO2 and T to convert this carboxylic acid into the acid halide with chlorine here, giving us our final products here. Now for part B, we are given a series of reactions and a reactant here. So the first step here, we're given Mg ether, which will insert itself between the carbon and chlorine here. So what we'll get is that we'll get this. This acetal here. And then we have MgCl. And this is a Grignard right here, where the carbon attached to the MgCl is partially negative. And then for the second step, we bring in our CO2, which is this right here. And since this carbon here is attached to two electronegative atoms, this carbon is electrophilic, where the nucleophilic carbon here can attack the electrophilic carbon and then kick up that double bond oxygen to that oxygen atom right there, giving us this product here, where now the MgCl dissolves in the solution. We have a the pink carbon is now attached to the blue carbon, and we see that the blue carbon has an O- group and a carbonyl group there. Okay, and then the third step, we bring in our acid to protonate that negatively charged oxygen to neutralize it, and that gives us our carboxylic acid. And I'm going to redraw the carboxylic acid in this way here. Okay, and then now the acid also not only it does it protonate this negatively charged oxygen, it also deprotects this acetal group into the ketone. And then you could look at the mechanism online, but I'm just going to keep going forward here. And then for the next step, we have NaBH4, which is a reducing agent. So we see that we could reduce this carbonyl down into the alcohol with after the NaBH4 step. Okay. So then after the NaBH4 step, we have this reduced carbonyl to the alcohol there, this carboxylic acid. And then the fifth step, we add acid and heat, which will protonate this carbonyl oxygen. And after that, oxygen gets protonated, we activated this carbonyl, where an intramolecular reaction is going to happen now, where this alcohol is going to attack the electrophilic carbonyl and kick up the double bond onto that oxygen right there. And then I'm going to label the atoms here now, where we have atom 1, 2, 3, 4, 5, 6. Made a 6-membered ring. And that would give us okay. And then where this oxygen here is our 1, 2, let's see, 1, 2, 3, 4, 5, 6 here. And then now we see that on our 6th carbon, we have 2 OH groups. Okay, and then I'm going to move on with the new page because I'm running out of space here. Into a new page. Okay. And now we see that this carbon here is connected to 2 electronegative oxygens, which is very unstable. So we could bring in our other excess H3O plus acid to protonate one of the OH. That would give us this good leaving group OH2 plus now, and this OH. And after we have the good leaving group, we could reform our carbonyl from this alcohol here, and then kick out the good leaving group at the same time. Okay, and then the very last step here is to reform our acid catalyst with the water conjugate base. And that would give us our final product here. Okay. Now let's move on to the next problem. Now we see here that we have the Jones reagent as the first step, which is an oxidizing agent and would oxidize this aldehyde all the way down to a carboxylic acid. Then the next step of PBr3 converts the carboxylic acid into the acid halide with bromine. And that is our final product. Okay, so now let's move on to the next problem. We see here that we have a strong base, strong nucleophile OCH3 minus or OH minus, which will deprotonate this hydrogen and give that oxygen a negative charge. Okay, and then now we have our nucleophilic oxygen here with the electrophilic carbon here bonded to the good leaving group bromine, where we could do SN2 reaction, attack that electrophilic carbon, kick out the good leaving group bromine, and then we would get the CH3O here as the final product. Now let's go over the next problem. We see here that we have Na plus Cl minus, which are spectator ions, and this right here would give no reaction. So if you wanted to convert this carboxylic acid into an acid halide with chlorine, like this product here, if you wanted this product instead, the reagent you would use is SlCl2. Now let's move on to the next problem. Now this is the mechanism of this intramolecular reaction here. So we see that we're given acidic conditions with the proton here. So what we would do is we would protonate the carbonyl oxygen with that proton. Okay. And after we protonated this carbonyl oxygen, we activated this carbonyl carbon and made it more electrophilic, more partially positive. So then this weak nucleophile here, neutral oxygen, is able to do an intramolecular reaction where the nucleophile is on the same molecule as the electrophile and attack itself. Then to help figure out what's connected to what and what how it's connected, I like to number our attacking atom to the atom being attacked. So this is going to be atom 1, 2, 3, 4, 5, where we form the 5-membered ring, with oxygen being the first atom. 1, 2, 3, 4, 5. And then I see what is attached to which atoms. Atom 1, we see that we have another hydrogen, giving that oxygen a positive charge. Atom 3, we have a methyl group. And then atom 5, we see that we have a we have this as well. Don't forget the alcohol of the carboxylic acid. We have 2 alcohol groups on atom 5. Okay, and now we do a proton transfer step where we're going to deprotonate this group and protonate this group at the same time, because we see that this carbon here is very unstable, this tetrahedral intermediate, since it's attached to 3 electronegative oxygens, 1, 2, 3, making it very unstable. So what we're going to do is that we're going to do a proton transfer step here, where we protonate the group that we want to leave and deprotonate the group that we want to stay. So then we have this neutral oxygen now, and this good leaving group OH2 plus. Then we could reform our carbonyl and then kick out our good leaving group OH2 plus there. And then that would give us almost our final products, because we still have this hydrogen on the oxygen right there, giving this oxygen a positive charge. And so we could reform our acid catalyst by using the water that just left, deprotonate that oxygen, and give us our final product here. Okay, now let's move on to the synthesis problems here. We see here that we started with a chain and we broke open that chain with 2 carboxylic acid derivatives. So we could say that these acid halides came from a carboxylic acid in the previous step, where this reacted with PBr3, 2 equivalents or in excess, to give us our final product. So what we could do is that we could break open this ring with an ozonolysis reaction with this double bond here. So, or this double bond here. And to figure out which double bond we want to break open, we count how many carbons we have on the end products. So we see that we have 1, 2, 3, 4, 5 carbons. So let's say we have a double bond there, where when we do ozonolysis, we cut that open, form the aldehyde there. We're going to have, let's say, 1, 2, 3, 4, 5. Where at carbon 2, we have a methyl group. So that shows that we want the double bond on the Hoffman side here. So that means that for the E2 reaction to form the double bond, we want it on the less substituted space. So we have to use a bulky base in order to form this less substituted double bond instead of this more substituted double bond. So the bulky base that we could use is this butoxide here. And its solvent. So what that does is that it would deprotonate this hydrogen, form a double bond there, kick out the good leaving group bromine there. So that would give us this alkene there. And then we do our ozonolysis reaction, where we would snip up this double bond, add a carbonyl there, and then we would get this molecule. And then I'm going to redraw this to make it neater. We have 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4, 5. And this is 1, 2, 3, 4, 5. And we see that at carbon 2, we have a methyl group coming out of there. Then from the last step, to convert this aldehyde into this acid halide here, we would have to first fully oxidize this aldehyde into a carboxylic acid using Jones reagent. So that would be carboxylic acid here. That, OH. And now from the carboxylic acid to the acid halide, we could use PBr3. Okay. So there would be 5 steps here. So then the first step here is to do the E2 Hoffman reaction to form the double bond on the less substituted side. The second and third step is the ozonolysis reaction, where we snipped up the alkene in half and give it a carbonyl. Then we oxidize this aldehyde down to the carboxylic acid using Jones. And then we converted the carboxylic acid to the acid halide using PBr3. Okay. So for this next synthesis problem, we see that we converted this alkyl group into the ester group. So we could infer that this ester group came from the carboxylic acid. And to convert this alkyl group to a carboxylic acid, we know that this R group has at least one benzylic hydrogen, which means that if we react it with KMNO4, H2O, and heat with the acid workup, then we're going to oxidize this alkyl group with at least one benzylic hydrogen to a carboxylic acid. Okay. And then to convert this carboxylic acid to the ester here, then we would have to do it in acidic conditions with heat, since this reaction would not happen by itself, with the alcohol giving the ester that we want, which has 1, 2, 3 carbons, 1, 2, 3 carbons. And the mechanism is nucleophilic acyl substitution. And the most common pattern for these mechanisms is that you protonate the group that you want to leave and you deprotonate the group that you want to stay. Okay, so now let's go over the next synthesis problem. We see that we converted this halogen into an acid halide where the stereochemistry is inverted. So we could infer that this acid halide came from the carboxylic acid, and that carboxylic acid could come from hydrolysis of nitrile. So we could say that this chlorine got converted to a nitrile. via SN2 reaction, which is why the stereochemistry will get inverted. Then we are going to hydrolyze this nitrile using acid and heat, which converts the nitrile into the carboxylic acid here, where this carbon of the nitrile is this carbon of the carboxylic acid. And then it still has the dashed stereochemistry. And then to convert this carboxylic acid to the acid halide, then we would use SOCO2 with the pyridine solvent, which would give us this side product here. Okay, and now I'm going to go over the mechanism of converting this carboxylic acid to the ester, which is esterification. So let me draw out this benzoic acid here. And then we have acid, heat, and this alcohol here. So since we're in acidic conditions, we're going to protonate the carbonyl oxygen. To activate the carbonyl carbon. And since we activated this carbonyl carbon, the carbonyl carbon is now more electrophilic for this weak nucleophile alcohol here to attack and kick up the double bond onto that oxygen, giving us kick up the OH on the other side. And then I like to star the attacking atom, dot the atom being attacked. They're now bonded together, the dotted atom and the starred atom. And I see what's attached to the starred atom now. I see that one hydrogen is attached to it, and I see 1, 2, 3 carbons attached to it. 1, 2, 3. Now this oxygen has a positive charge. Now this is where the protonate the group that you want to leave and deprotonate the group you want to stay comes in to play. So we want this OH group to leave because we want this ester group to stay. So then we're going to do this proton transfer step here, where we can just protonate the group we want to leave and deprotonate the group we want to stay at the same time. Some professors want you to do it in separate steps, but this way saves more time and do it in one step rather than 2 steps. So I will check with your professor notes and ask them. And then we have this good leaving group now, and then OH here, then this neutral group there. So now, since we have a good leaving group, we could reform our carbonyl, kick out the good leaving group at the same time. And then we almost have our final products here, where the last step here is to just deprotonate this positively charged oxygen with the water leaving group that's left and reform our acid catalyst, giving us our final ester product here. Yep, and that is the mechanism for this synthesis problem over here. But you don't need to draw the mechanism for the synthesis problem. It's just the steps. But I drew out the mechanism to explain how we converted this carboxylic acid to the ester.